Hello, viewers of the world, my name is Annie. And that is Robert.
Sup.
And we're here to talk to you about the gas laws.
So listen up.
Before doing gas law calculations, we've got to figure out what all of the appropriate terms, symbols, and variables are. For those of you having trouble figuring it out, here are some of the more common ones.
Ideal gas, an imaginary model of a gas that has a few very important properties. These properties are that the particles of the gas are assumed to be infinitely small, the particles move randomly in straight lines until they bash into something, another gas molecule or the side of whatever container they're in. The gas particles don't interact with each other. They don't attract or repel one another like real molecules do, and the energy of the particles is directly proportional to the temperature in kelvins. In other words, the higher the temperature, the more energy the particles have. We make these assumptions because A, they make the equations a whole lot simpler than they would be otherwise, and B, because these assumptions don't cause too much deviation from the ways that actual gases behave.
Kelvins, a temperature scale in which the degrees are the same size as degrees Celsius but where 0 is defined as absolute zero, the temperature at which molecules are at their lowest energy. To convert from degrees Celsius to kelvins, add 273.
By the way, we don't say degrees Kelvin, we just say kelvins. Go figure.
Pressure, a measure of the amount of force that a gas exerts on whatever container you've put it into. Imagine a shaving cream can. When the pressure is high in there, the gas in the can pushes very hard on the walls of the can, which is why the cans are made much stronger than soda cans. Units of pressure include atmospheres. 1 atm is the average atmospheric pressure at sea level, torr, which are equal to 1/760th of an atmosphere. Millimeters of mercury. 1 millimeter Hg is the same as 1 torr, or 1/760th atm, and kilopascals. There are 101,325 in 1 atom.
Standard temperature and pressure, a set of conditions defined as 273 K in 1 atom. Also temperature, a measure of how much energy the particles in a gas have. Units of temperature that you'll run into include degrees Celsius, which you shouldn't use when doing gas law calculations for reasons we'll talk about later, and kelvins, which is equal to 273 plus the degrees Celsius.
There's also volume, the amount of space that some object occupies. The unit of volume can be cubic centimeters, abbreviated cc, or centimeters too. Milliliters, abbreviated milliliters, -1 milliliter is the same as 1 cubic centimeter. Liters, abbreviated as L, and equal to 1,000 milliliters, or cubic meters, abbreviated square meters. There are 1 million cubic centimeters in a cubic meter.
But Annie, what about the other laws?
Oh yeah, thanks for reminding me, Robert. There's also other laws like the Avogadro's law. Amadeo Avogadro was a man with a dream. He knew that if he studied and practiced and worked really hard, he could be the world's most famous tuba player, renowned throughout the modern world for all time. Tragically, his dream died during a freak tuba accident in the early 1800s. Though he was able to regain the use of his tuba hand, it never recovered enough for him to gain superstar asterisk. Heartbroken, he turned to science, coming up with a law that we use today, called, straightforwardly enough, Avogadro's law.
Don't forget Boyle's law, Annie.
Alright. Robert Boyle was another man with a dream. He wanted to be the first man to eat 100 hard-boiled eggs in a 24-hour period.
Ooh, that sounds delicious.
Shut up and let me talk, why don't you? Anywho, back to the story. Unfortunately, some of the other chemists got jealous. Let's just say that considerable ugliness ensued and Boyle's dream was permanently derailed. However, Boyle was a man of many talents, and was able to come back from his humiliating egg fiasco asterisk to come up with a gas law of his own.
Hey Annie, can I ask you a question?
Sure, go ahead.
If we have 4L of methane gas at a pressure of 1.0 atm, what will be the pressure of the gas if we squish it down so it has a volume of 2.5 L?
That's easy, okay? Let's plug the numbers we've been given into the problem. P1 is 1.0 atm and V1 is 4L. After we squish the gas, the volume, V2, is 2.5 L. When we put all of these numbers into the equation, we get 1.0 atm 4L equals X atm 2.5 L X equals 1.6 atm.
Can I say Charles Law now?
Sure, why not?
Okay, Jack Charles was a disturbing and scary guy. Though he came up with a really handy law for determining what the relationships between the volume and temperature of a gas are, his private life was far more bizarre.
There is also Gay-Lussac's law.
Huh?
Oh, grow up. There was a third guy whose gas law is a little less famous than the others. Some think it's because of his funny name, while others think it has something to do with having a bad public relations firm working for him. Whatever the reason, his name is Gay-Lussac, and his law related pressure to temperature, P1 divided by T1 equals P2/T2.
Here's the combined gas law. Imagine a world in which you didn't need to memorize the three laws above. Instead, there was one big law that covered both of them. Hey, that's the world you live in now, and the law you need to know is the combined gas law. P1V1 divided by T1 equals P2V2/T2.
The ideal gas law is an equation of state, which means that you can use the basic properties of the gas to find out more about it without having to change it in any way. Here's the equation. PV equals nRT. One of the main problems that beginning chemistry students have is in doing conversions between grams, moles, and molecules or atoms.
Here's an example. How many moles are in 22 grams of copper metal?
In all problems like this, you need to go through 4 steps to find a solution. The 4 steps to solving moles problems are this. Step 1. Figure out how many parts your calculation will have by using the diagram. Looking at the diagram above, we can see that we are going between grams and moles, which is a 1-step conversion. Furthermore, we can see that we need to use the atomic mass of copper as our conversion factor.
Step 2. Make a T-chart, and put whatever information the problem gave you in the top left. After that, put the units of whatever you were given in the bottom right of TET, and the units of what you want to find in the top right. In this case, the problem gave you 22 grams of copper as the starting information. Because this is what you were given, put 22 grams of copper in the top left of the T. Since grams of copper is the unit of what you were given, put this in the bottom right of the T. Since you want to find out how many moles of copper are going to be made, put moles of copper as your unit in the top right.
Step 3. Put the conversion factors into the T-chart in front of the units on the right. As we saw from the map, the conversion factor between grams and moles is the atomic mass of copper. Because we measure atomic mass in grams, you need to put the atomic mass in front of the unit grams of copper. What do you put in front of moles? Whenever you do a calculation of this kind, you need to put 1 in front of moles.
Step 4. Cancel out the units from the top left and bottom right, then find the answer by multiplying all the stuff on the top together and dividing it by the stuff on the bottom. In this case, you'd multiply 22 by 1 and divide the result by 63.5. Your answer, 0.35 moles of copper.
Hey Robert, this time I've got a question for you.
Alright, shoot.
If I have 4 liters of a gas at a pressure of 3.4 atmospheres and a temperature of 300 K, how many moles of gas are present?
Great. The first thing you need to do is figure out what value of the ideal gas constant should be used. Since pressure is given to you in atmospheres, use the first one, 0.8206 Lx atom divided by mol xk. After plugging in the given terms for pressure, volume, and temperature, you end up with 3.4 atom 4L equals N 0.08206 Lx atom divided by mol xk 300 K N equals 0.55 moles.
Well, I guess that's all the time we have left.
Yeah, I guess so.
Goodbye for now everyone. This is Annie and Robert signing out.